Okay, in this lesson, we are going to discuss about polygons. First thing, let me start by defining what's a polygon. So you need to know what's a polygon in order to understand the properties and whatever happens related to polygons. Instead of going into definition, let me point out few criteria that has to be fulfilled for a 2D figure. So that would have been one of the properties any which way. For a 2D figure to be classified under the category of a polygon. So first, yes, so it has to be a 2D closed figure. So it cannot be an open one. So it has to be a closed figure or bound. It has to be bounded. Second, everything in the boundary, let's say, should be straight lines. There will be turns on it, but all the turns will be, with an angle, not a curve. So there'll be straight lines always. So no curves allowed. And the third one, this is important. You cannot have the sides, so basically the ones which are in the boundary. So the sides cannot intersect anywhere except the vertices. What I mean by that. So let me show you an example. If you consider a polygon like this, so this satisfies all the criteria, right? So this is a closed figure, all straight lines. Consider these are straight lines, by the way. The sides are not intersecting except the vertices. So these are the vertices, right? And the sides are actually intersecting only in the vertices, not anywhere inside. But consider a figure like this, let's say. So again, consider them to be straight lines. So it qualifies these two criteria. It is a closed figure, as well as the boundary are all straight lines, right? But the sides are actually intersecting except the vertices also. So this side and this side is intersecting inside, right? I mean, it's intersecting apart from the vertices. Now, if you call this as vertex, then this will be a different side, and this will be a different side, and this will be a different side. But how can these two be different sides? So that doesn't make sense any which way. If I highlight one part here, so this section of this figure is definitely a polygon, right? It qualifies all the criteria. So that is the basic understanding of polygon. So this is the definition of a polygon. What we are going to majorly do in this particular lesson is work on some angle related ideas when it comes to polygons. This is the interesting part of polygons. Now we are going to use some basic ideas and just keep one of your pens ready, not to write anything, but let's do something interesting now. And let me draw one figure for that. Let me take these things off. Okay, the first thing that we are going to do is we are going to work on exterior angles. Now, first of all, what are exterior angles? Before we get into that, I've extended each of the sides because that is the part of the definition of exterior angle. So exterior angle is basically angle between any side extended and its adjacent side. So for example, if you look at this figure, so let's consider this side. Once it is extended, the angle between this side and the adjacent one. So this is the exterior angle, not that this completely outside one is exterior. That is incorrect. So basically, if we take the pairs of interior and exterior, so each pair of interior and exterior will add up to 180 degrees. So that is the idea. So interior and exterior add to 180 degree for any vertex. So if you consider any vertex, the interior and exterior will add up to 180 degrees. So this is one idea you can keep in mind. Now I hope you have your pens ready. As I said, I mean, you don't have to work anything on the notebook. It's just for a visual idea. Let me consider all the exterior angles here. By the way, I could have extended this side and taken this. I mean, this one will be same as this one, right? If you remember the very basic ideas that we discussed in the very first lesson of geometry. These are one set of exterior angles. So take your pen and make it point in this direction. So now what you do is just move along this angle. So this angle, when you move in this direction, now you should be on this line and pointing on this direction. Your tip of the pen should be pointing on this direction, right? Similarly, move this angle. So once you move this angle, your pen will be pointing in this direction, right? So it will be pointing in this direction. Complete this. So move this angle. Your pen will be pointing in this direction. Complete this angle. your pen would be pointing in this direction. And finally, when you complete the last angle, you're back on the same line wherever you started from. And also your pen is pointing in the same direction. So basically your pen just moved one complete circle, right? Or in a way, if you add all the angles that the pen moved, it should be a total of 360 degrees. So this is the first idea that you have to remember. And this is a very fast technique also. Whenever it comes to, angle related question in polygons, for a minute, just think about the exterior angle. So that is fast because as you check, the sum of the exterior angles will always be equal to 360 degrees. So you rotated a total of 360 degree, right? Now, I hope you understand. I mean, this has nothing to do with the number of sides of the polygon. Once you make these angle rotations, whatever be the number of sides of the polygon, you can try this yourself in your notebooks and all. Try to take a different polygon of different number of sides and just keep rotating. So once you complete the rotation, you will always land back on the one you started with and also on the same side. So basically the sum of exterior angle is always 360 degree, irrespective of the number of sides of the polygon, irrespective of n, let's say n being the number of sides of the polygon. So this is about exterior angle. Let me also discuss about interior angle. Let me draw another figure. So interior angles. So interior angles are basically angle between any two adjacent sides. So I'm defining interior angle, by the way. Yeah, so interior angle is angle between any two adjacent sides. Obviously, it's not mandatory that all the interior angles will be equal, but it could be equal. That is fine. But these are the interior angles that we're talking about. Now, this sum of these interior angles can be actually figured out from whatever we have derived here. So sum of the exterior angles is 360 degrees. That is irrespective of n, but then we can derive it from there also. But what I'm trying to do is I'm trying to do it independently of that. So you should know the direct approach any which way for both of them. So this is the direct approach for exterior ones. Let us try to understand the direct approach for interior ones. Very easy. Just use triangles. So what you do is you just pick any vertex of your choice. It doesn't matter. And from that vertex, draw all the diagonals you actually can in the polygon. So in this case, for example, from the vertex that I picked from up top, so from this particular vertex, I can manage to draw a couple of diagonals here, right? Not more than that. Let's discuss for a minute why so. There are 5 vertices here, right? In this case, because they're a 5-sided polygon. Now, from this vertex, I cannot draw a diagonal to this one, the one adjacent to it, or this one, or itself. So obviously these 3 vertices cannot be connected from this particular vertex. Everything except from that can be connected. So there are 2 more vertices. So those 2 vertices can be connected via a diagonal from this particular vertex, right? So if I try to generalize it, let's say, so suppose there's a n-sided polygon. You pick any vertex. From any vertex, you can connect n minus 3 other vertex, right? The one itself cannot be connected and the 2 adjacent cannot be connected. So n minus 3, the remaining. So if there's a 6-sided polygon, you can connect 6 minus 3, 7-sided polygon, 7 minus 3. So you can connect that many diagonals. So any vertex will be connected to n minus 3 other vertex to give us diagonals, right? So these are the diagonals from any vertex. Now, whenever we are drawing these diagonals, what happens is each diagonal is behaving like a partition between 2 adjacent triangles in this figure, right? So I hope you can see this. I mean, this diagonal behaves like a partition between these 2 triangles, and this diagonal behaves like a partition between these 2 triangles. So if you consider there are n minus 3 diagonals, there has to be n minus 3 plus 1 triangle. For instance, in this figure, there are 2 diagonals, 1 and 2, and there are 3 triangles, right? So there will be 1 more triangle, something like that. So effectively, the number of triangles that will be formed will be n minus 2. Now, please understand, this is not same as how many triangles we can form. We can actually form a lot of different triangles here. But the point is, from one vertex, if I draw all the possible diagonals, then there are n minus 2 triangles being formed. And now coming to the requirement here. So we are looking for the sum of the interior angles, right? As we have done for exterior angles. So sum of the interior angles will basically be the sum of all the interior angles of these triangles, right? So if I add all the interior angles of this particular of these triangles, all of these triangles, even here you can see combined we are getting this angle. In this case combined we are getting this angle. So each of the cases we are getting these angles, right? So the sum of the interior angles, will be n minus 2, that many triangles, and each triangle having 180 degrees, right? So you have these many triangles and each triangle having 180 degree in it. So if you add all of this, you get the sum of all the interior angles. So just to summarize everything that we did, so let me just put this also highlighted. So for interior angles, so this is what we know. Yeah, so for interior angles, you have this sum here, right? Sum of the interior angles will be given as n minus 2 into 180 degrees. So I hope you can see that this is not irrespective of n. This depends on the value of n. So depending on the value of n, the sum of interior angles will change in any polygon. You can take an example of a quadrilateral. It has 360 degrees, right? 4 minus 2, so 2 into 180. This was an example of a pentagon. By the way, coming to the name, so quadrilateral is 4, a triangle is 3. Triangle is also a polygon, by the way. It satisfies all these three criteria that we talked about. These three criteria that we discussed earlier. So basically, triangle is three-sided, quadrilateral is four-sided. Anything above is something gone. So 5 is pentagon. 6 is hexagon. 7 is heptagon. 8 is octa. 9 is nona. So these are two things that you should be remembering and independent of each other. Okay, so this is the question. So there's a polygon having each interior angle equal to 162 degrees, and we are looking for the number of sides of the polygon. By the way, if you just look back into this figure, this had 5 sides, both of these. So this was a pentagon. This has 5 sides. So because this has 5 sides, this will have 5 vertices. And because this has 5 vertices, each vertex will have a interior angle and will have an exterior angle. If you remember this part, interior and exterior adds up to 180 degree for any vertex. So basically, what does it signify? That each vertex will have one interior angle and one exterior angle, right? So coming back to this question, so you have a polygon having each interior angle equal to 162 degrees, and we're looking for the number of sides of the polygon. Now, because it says each interior angle is 162 degrees, so we can understand that all of them are equal and they are equal to 162 degrees. In terms of interior angle, if you think about the sum, it depends on the number of sides, right? But if you think the same thing in terms of exterior angle, so if each interior angle is 162 degree, then each exterior angle, now remember that pair thing that we discussed earlier, any vertex interior and exterior adds up to 180 degree, right? So each exterior will be 180 degree minus 162 degree, which is equal to 18 degrees, right? So you have 18 degrees each exterior angle. And now because independent of the number of sides, the sum of exterior will always be 360 degrees. So in order to figure out the number of exterior angles, all we have to do is count how many 18 degrees will be required to fulfill that 360 degree, right? So 360 divided by 18 will suffice. So basically 20 sides of or 20 exterior angles. So that means there are 20 vertices, which implies there are 20 sides of the polygon. So this is what I was talking about. So when you have anything related to this angle related question, so try to think in terms of exterior angles. So exterior angles is a fun way to actually, figure out the answer. It might be a little fast. You can actually have negative exterior angle as well. So let me draw a figure for you. Okay, so I've just drawn a random polygon. By the way, this is a polygon. It's not a bird. Uh, it satisfies all the criteria here. You can check this out. It's a 2D closed figure. Everything in the boundary are straight lines, and the sides are not intersecting except the vertices. So these are the vertices. Okay, these are actually the vertices. It doesn't intersect. None of the sides intersect anywhere except the vertices. So in these cases, by the way, this has a name. This is known as a concave polygon. A concave polygon is a polygon where at least one angle is a reflex angle. So anything more than 180 degrees reflex angle, if you remember the name. Only when all the interior angles are less than 180, in that case, I mean, these examples that we took earlier, That's a convex polygon. So this is an example of a concave polygon. If you remember the definition of the exterior angle, so the definition of exterior angle says any angle between a side extended and the adjacent side, right? So now, if you consider the cases where there are reflex angles, if you extend any of the side, either this one or this one, doesn't matter. So let's say I extend this one. Now the angle between this extended side and the adjacent side is inside the polygon itself, right? But that violates the condition of the exterior thing, right? When exterior by name, it should be outside, isn't it? Now, because this is inside the polygon, we are going to consider this as negatives. So we are going to consider this exterior angle as something negative. Now, there are some more reasons behind it. I'll give you two more ways to understand this. So one of those is this one. Any vertex interior plus exterior has to be 180-degree. So for example, let me take the interior angle in this case. So this interior angle is actually more than 180, right? So if I take this as the interior angle and this as the exterior angle, if I add these two, if I consider this as positive, the sum cannot be 180, right? So in order to get the sum as 180, what I need to do is I have to subtract this exterior from this interior angle. Then what happens is this part goes off and what you have remaining is actually 180 degrees, right? So this is one reason. One other reason, that is. The third reason that I can give you is, if you remember that idea of exterior angle rotation, so just connect this exterior angle. So this is the exterior angle movement. Let's say this exterior angle, this is the movement here. You can consider this one also. This is the movement. So these are all of the exterior angles where you have this thing. I mean, the interior is not a reflex angle less than 180 degree. So not a concave one. So I'm going cyclically. So I should take this one. I'm taking clockwise, that is. So these are all moving clockwise, isn't it? So this is clockwise, this is clockwise, this is clockwise, this is clockwise. But check this out. I mean, wherever you have this reflex angle. So after you make this rotation here itself, you are on this line, right? Now, in order to come to this line, you need to rotate backwards, right? You have to rotate anti-clockwise. Only then you will be coming to this line. After that, you rotate this direction again clockwise. So this is again clockwise. So these are getting added, right? But this is like subtracted. You move backwards. So that is one other justification why extreme angle in this case will be considered negative. So hopefully that was understandable by you lot. So in this case, what you're gonna understand is whenever the interior angle is more than 180, the basic idea is, in order to justify interior plus exterior is equal to 180 degrees. And because the exterior is inside the triangle, the polygon, so in that case, we should consider the exterior as negatives. But this will always hold true, even in case of concave polygons, as I said. I mean, interior angle, suppose this was interior angle was 240 degree, this angle, or let's say 270 degree. This seems more like 270. So if this is 270 degree, we will consider this exterior angle to be minus 90 degree. Only then 270 plus minus 90 will actually be equal to 180 degrees. So this will automatically satisfy. So that's all I had to discuss related to this concave polygon. There might be questions on basis of this also. Be careful on that part in terms of exterior angle. One last thing before we move ahead, we will be discussing a little bit more about it on the next lesson. But let me define for you a regular polygon. Now, when I was writing the previous question, I mentioned that all the angles of this particular polygon, each interior angle is 162 degree, right? So because each interior angle is equal to 162 degree, it is not necessarily a regular polygon. Please understand that. For a polygon to be called regular, there has to be met that it has to meet two criteria. All angles must be equal, and there's an and, not a or kind of thing. All sides must be equal. That's the definition of a regular polygon. So regular polygon should be symmetric in nature. Just the angle being equal doesn't make it symmetric. For instance, I mean, it's only in the case of triangle that if all the angles are equal, then all the sides are automatically equal, and vice versa. It's not necessarily true for any other higher polygon. So not even for quadrilaterals. For example, if you consider the case of quadrilaterals, I can consider, let's say, a rhombus which has sides equal, but angles not necessarily equal. Maybe equal, may not be equal, right? If you take a rectangle, in this case, the angles are equal, all are 90-degree. Interior angles are equal, but the sides not necessarily equal, maybe equal, may not be equal. If both are equal, then that becomes a square. Now, square is actually a regular polygon. So this is definitely a regular polygon, not necessarily a rhombus or a rectangle. So I hope you understood this idea of regular polygon. We will discuss a little bit more about regular polygons, two special regular polygons in the next lesson. But that's it. That's all I had to discuss related to the basics of polygons. Hopefully this was understood related to interior and exterior angles, how it is useful, and concave polygon especially, and regular polygon especially. So that's it for this basic lesson. I hope everything was understood. Thank you for joining in.